density as a function of the pressure of the blob at the new location and the entropy of the blob at the new location. Those things must be related to each other, and that's simply going to be equal to density, pressure at R plus H because it's in pressure equilibrium, and S of R because the entropy of the blob has stayed fixed at its original value specified by the conditions of the surrounding medium at the location R, not R plus H, right? Where it started down here at the bottom. Okay, so we haven't solved anything here. We just identified that I can specify the density as a function of pressure and entropy, right? That is simply one of the fundamental thermodynamic properties that relates all of these things together via the equation of state. Now, at this point, we can apply Archimedes' principle, right? That is, that if the density of the blob at R plus H is greater than that of its surrounding medium, if it's denser than the medium it finds itself in, then it will not be buoyant, just like our boat, right? If the total density of the object that is trying to float is greater than water, meaning it doesn't displace more water than it weighs, it'll sink. Same with our blob. If the blob rises, maintaining pressure equilibrium, but remains denser than the surrounding medium, then it will not experience a net buoyant force. It'll fall back down. And so those are the scenarios in which we're going to find convective stability. You're not going to maintain this sort of motion. What we want in order for something to become convective is for it to experience a runaway buoyant force, meaning that I perturb this thing up some distance, it maintains pressure equilibrium by expanding, and in so expanding, it becomes slightly less dense than the medium that it now finds itself in. Therefore, it experiences a net buoyant force upward and runs away. And that would be the start, the onset of convective instability and ultimately convection that lasts a sufficient period of time to transport heat in a star. So that's the idea. Okay, so therefore, for stability, we require the following. We require that the density of the blob at its new location be greater than the density of the medium at that new location. Plugging in what we had before, that means that the density of the pressure at R plus H and the specific entropy at R, using the thermodynamic relationships in the equation of state to invert these things and relate them to each other, must be greater than the density as a function of the pressure at R plus H and the entropy at R plus H. Simply that. So if that condition is satisfied, the blob will be restored to its original location after we perturb it a little bit and kick it up. However, if that condition is not satisfied, the blob will continue to rise forever. Okay?